Greetings and welcome. Today we're taking a look at products and quotients of complex numbers, which technically that we've done before where we've multiplied them in rectangular form, a plus bi times another a plus bi, where we just essentially FOIL that out, or dividing them where we have to multiply top and bottom by a conjugate. But today we're going to multiply and divide complex numbers that are in polar form. So that's what we're specifically going to analyze today. So I've got a little derivation of the product. So I've got two complex numbers in polar form. Remember, this one could also be written as R1 CIS theta 1 if you wanted, for the cosine I sine sort of thing. That's the shorthand notation of it. So if I'm multiplying these two things, the first thing we did was we grouped R1 and R2. And I've taken these two binomials, so to speak, and I've essentially just FOILed them, right, or double distribution all of those into one another, and I end up, getting an I squared showing up and different things like that. So that's how I get from this line to this line. And now what we end up doing is we group our like terms. So the I squared is equivalent to -1. So then I'd have a negative sine theta 1 sine theta 2, and I ended up moving that over here. So I've got my real components, so to speak, of this complex number, and then I've grouped the two imaginary components over here, and I've factored out the I from both of them. And now this one might not be as obvious. You might have to remember some of your trig identities. This is the cosine sum identity, and here's the sine sum identity. So I end up replacing both of those as such, and that gives me the equation or the formula that is going to allow me to find the product of complex numbers in polar form. So more officially here, if you want it, this is what it would look like. Let's see. Oh, I'm opening Excel accidentally. That's just fine, though. So let's paste this. And here we go. So the product of complex numbers in polar form, if I'm multiplying two of them, right, where I've gotten R1 theta 1 and R2 theta 2, you multiply R1 and R2 to find your modulus, or the distance from the origin to your point, graphically speaking. And the argument, or the amplitude, is just going to actually end up being the sum of your angles. So you add the angles and you multiply the moduli, I believe is how I would pluralize that. So let's do an example of this where we're going to find the product, and then we're going to end up taking that product and writing it back in rectangular form. So here's our little example. Find the product, then write the product in rectangular form. So here's two complex numbers written in polar form, and the first thing I'm going to do is I'm going to piecemeal this, where I'm going to find my new modulus. So R is going to equal the R1 times the R2, essentially. Actually, I might even write that in green. You could even almost view this as like a little formula. And my new amplitude is just going to be the sum of the previous amplitudes. All right, so we'll calculate each of these first, and then we'll put it in the right form. So my modulus is 3 times 2, which is 6. And my amplitude is going to be 7 pi over 6 plus 2 pi over 3. So theta is going to equal, well, I'd need a common denominator here, so I'd multiply this by 2 over 2, giving me 4 pi plus 7 pi is 11 pi over 6. So using these, I can now write the equation, right? Essentially just this right here. It's going to give me my result in polar form. So I'm going to have 6 times, and I'm going to have cosine of 11 pi over 6 plus I times the sine of 11 pi over 6. So this is actually my answer in polar form of this complex number. So you can see I've just merely gone and plugged in the values here for each. It's got the real part, it's got an imaginary part, it's got the modulus out here out front. And if I want to now convert this back into rectangular, I'm just merely going to have to evaluate the cosine and sine values and then just distribute the 6 into it, so to speak. So, so this is equal to 6 times, let's see, cosine of 11 pi over 6. That's going to be the positive cosine. Let's see, 11 pi over 6 is almost 2 pi. All right, it's just negative pi over 6 is another way I could view it. It's in the fourth quadrant, so it's positive cosine of pi over 6 plus I times and sine of 11 pi over 6. The reference angle is still pi over 6, but it's negative in this case, so negative sine of pi over 6. And pi over 6, of course, is roughly exactly, actually, 30 degrees. So 6 times cosine of 30 degrees, or pi over 6, is root 3 over 2, plus, or actually I'll just write the minus, sine of pi over 6 is 1/2. It's got the negative there, times I. So for rectangular form, now I just merely distribute. 6 divided by 2 is 3, 3 roots of 3, and 6 divided by 2 is 3, so minus 3i. So here is rectangular form as well as polar form of the product of those two complex numbers. So that's product. Let's now take a look at quotient. And this one's going to be a little bit trickier for a derivation. I'll do that over here. So if I want to divide two complex numbers, now you probably don't have to write this down, these derivations. So I've got two complex numbers, I'm dividing them, right? It's got R1 theta 1s and R2 theta 2s. And what I would do, because I've got an I in the denominator, is I'm actually going to multiply top and bottom by the conjugate, specifically of just this portion here. I'm fine with the R2 being down there. At least in this case, we're assuming R2 is some non-irrational number. So we multiply top and bottom by the conjugate, just like we've done before. And up top, I distribute that all out, similarly to how we got the previous derivation. And I end up with grouping my real parts, I group my imaginary parts, all this and that. And in the bottom, I end up having a plus b times a minus b. So this is actually from the a squared minus b squared pattern, right? Where I've just plugged that in and I've distributed the square to the I and the sine and the cosine. Lots of superscripts and subscripts going on here. And now to go from this step to this one is a difference identity. This one is a difference identity. All right, giving me the value of sine difference there. And this, well, I squared is equal to -1, so that becomes plus sine squared. Cos squared plus sine squared, that's a Pythag identity. And that's just equal to 1. So my end result is just R1 over R2 multiplied by this right here. So let's take a look at an example of this. Or actually, first, let's write it down proper, give it a nice little name, make things look nice. So here we go, quotient of complex numbers in polar form. So when you're dividing two of those, you can see that my new modulus is just the quotient of the two previous moduli, and my new amplitude is the difference of the moduli, and it's also, by the way, notice the numerator subtract the denominator for that calculation right there. So let's do an example of this. And this ain't gonna be too bad, I don't think. And similarly to what we did before, we're going to find the quotient and then also express that quotient in rectangular form. So, in the case of a quotient, the new modulus, as we said, was going to just be R1 divided by R2. And the new amplitude is going to be theta 1 minus theta 2. So it's numerator angle minus denominator angle. Be careful with that. I know a lot of times we usually have like x2 minus x1 showing up in math formulas. So that is not the case here. And that could throw off, at the very least, the sign, S-I-G-N, of some of our trig values later on. So let's do this. So R is equal to 12 divided by 4, which is 3. Theta is going to equal pi over 4 minus 3 pi over 2. And in order to calculate that, I'm going to need a common denominator. So I'll multiply this one by 2 over 2, giving me, right, the 4 and the 4, which is what I need. And up top, I'll have 1 pi minus 6 pi. So that's going to be negative 5 pi over 4, if I'm not mistaken. So here I have my new modulus and amplitude, or argument, if you want to call it that, but no need to argue about it. So let's write this in the new form. So this is going to now be 3 times the cosine of negative 5 pi over 4 plus I times the sine of negative 5 pi over 4. And by the way, you could write this in CIS form for your shorthand abbreviation of cosine I sine. Cosine I sine. So there's polar form of this quotient, and if I want to then change this into a rectangular form, all I'd merely have to do is figure out the values of the sine and cosine and then multiply it out. So cosine negative 5 pi over 4, that's just a little bit bigger than pi, but in the negative direction. So that's actually second quadrant. Cosine is negative in that quadrant, and the reference angle is pi over 4, or 40 degrees if you're wondering. Plus I times the sine of an angle in the second quadrant is positive. So multiply by the sine of pi over 4, just like so. And obviously if I didn't know the values of these angles, you could use calculators to figure out some of this. So this is going to be negative root 2 over 2 plus, sine of pi over 4 is also root 2 over 2 times I. And so it looks like my end result is going to be negative 3 roots of 2 over 2 plus 3 roots of 2 over 2i. So now this is in my rectangular form, the a plus bi form, so to speak, where this is my real part, this is my imaginary part. If I wanted to graph this on the polar coordinate system, or the complex plane more specifically, my apologies, we would go left this value and up 3 roots of 2 over 2, which is the same as graphing right, negative 5 pi over 4 and out 3 is going to give us the same point in the complex plane. So, so thanks for watching, internet friends. Hope you all have a great day, complex or not.